Hello, we are Team 22018, and our project was to develop an electronically controlled continuously variable transmission, or ECVT, for the University of Arizona Baja Racing Team. Our project sponsor was Baja Racing and the Electrical and Computer Engineering Department, under the advisement of Dr. Michael Marsland. Hi, my name is Eric Duarte, and I'm the project lead.
My name is Lucas Creary. I'm the procurement lead and mechanical engineer.
My name is Micah Siegloff, and I'm the mechanical lead.
I'm Lance Casto. I'm a mechanical engineer.
My name's Andre Schreiber, and I'm the electrical lead.
My name's Brian Fairs, electrical engineer.
Baja SAE is an engineering team on campus that designs and builds a single-seat off-road vehicle to race against other schools in competition each year. The car currently uses a mechanical CVT transmission system, which consists of 2 adjustable pulleys and a rubber belt. In order to shift gears, the 2 pulleys actuate to change the radius of the belt and the overall gear ratio of the transmission. The shifting and the performance of the mechanical CVT can be altered by swapping out internal components like flyweights, springs, and ramps. This requires fully disassembling the system multiple times to properly tune the transmission and achieve the desired performance. The goal of the project is to replace the mechanical CVT with an electronically controlled CVT. An eCVT can be adjusted via a software update, which makes tuning and optimization much more efficient. Key performance parameters such as shifting and engagement with the belt can be more easily controlled and adjusted.
Our system requirements were segmented into performance, mechanical, electrical, interfaces, and system integration. First, we have RPM control, overshoot, undershoot. The goal of a CVT is to allow the engine to remain at peak power while it is shifting. The engine's peak power occurs at 3,600 RPM. Our requirement states that the engine RPM must remain within a particular margin of this RPM during shifting. Second, we have sensor accuracy. In order for the RPM of the engine to be controlled, it needs to be accurately measured. We set a requirement for the sensor to be within 5% accuracy of the engine RPM. Finally, we have our ratio range requirement. To achieve the appropriate vehicle torque and speed, the ratio range of the CVT must be in a range from 3.9 to 1 in low ratio to 0.9 to 1 in high ratio. Other key system requirements include the mechanical and electrical subsystem endurance, since the system needs to last the entire length of competition, and finally, adherence to SAE competition rules and regulations.
We began with several design options that revolved around the core actuation method of the CVT pulleys. The first was using linear actuators connected directly to the pulleys. The second was a hydraulic actuated system using hydraulic pumps connected to concentric slave cylinders. And our final option was a combination of hydraulic and linear actuator components with electronic and power components contained in a remote weatherproof enclosure. Ultimately, the third option was chosen for its durability, control accuracy, and ease of integration. Our final design is outlined as follows. The gear ratio of the CVT is controlled based off of the current engine RPM. The RPM is measured with a Hall effect sensor mounted near the primary pulley. We mounted 3 magnets on the primary, and the Hall effect senses each time a magnet passes by. From that, we can calculate the engine RPM. Our method of actuation uses hydraulic concentric slave cylinders attached directly to the primary and secondary pulley. The hydraulics are actuated via 2 master cylinders contained in a remote weatherproof enclosure. The master cylinders are compressed by 2 linear actuators, which move based off of input from 2 central controllers. This system leaves only the durable steel-braided hydraulic lines exposed to the harsh conditions of the track, with all of the electronics and other sensitive components contained inside of the housing.
Our main mechanical concerns revolved around the fatigue failure of the pulley and baseplate components, as well as friction produced by the fluid in the hydraulic lines. We performed simulations on pulley components to verify that the fatigue life meets the requirements for a Baja competition. The same was done for the hydraulic cylinder mounting plate. The master and concentric cylinders were selected based on actuation and fluid volume. Fabrication was done in and out of house. Major components such as the secondary pulley shaft and plate were machined and anodized by local companies in Tucson, while components used to integrate the system with the 2021 vehicle were fabricated ourselves.
The control scheme consists of 2 controllers, an engine RPM controller and a gear ratio controller. Together, these controllers govern the behavior and response to the CVT. The RPM controller was based on a differential equation for the overall vehicle dynamics and used the current engine RPM to output a desired gear ratio for the CVT. This gear ratio is sent to a PI controller, which uses the geometry of the pulleys and linear actuators to output motor PWM values. The motors move the pulley plates to a position that ensures sufficient belt engagement, efficiency, and gear ratio. This allowed for the RPM controller to be simulated in a non-linear state space form. This simulation showed that the controllers are capable of both maintaining our engine RPM at the peak power RPM and properly adjusting the pulleys to our range of gear ratios.
The electrical system consists of a network of 3 Teensy Arduino compatible microcontrollers that communicate via UART. The first microcontroller receives Hall effect sensor readings and calculates engine RPM. The second microcontroller performs gear ratio controller calculations and interfaces with the motor controller. The final microcontroller acts as the overall RPM controller and data logger. Our data logger records the following essential channels to an SD card during operation, which are used for issue diagnosis, tuning, and requirement verification. The microcontrollers are wired to a panel-mounted USB hub on the side of the housing, allowing for quick and easy flashing of code during tuning.
The system is powered with a 20,000 mAh LiPo battery. The motor controller is directly powered by the 14.8 volt supply. However, the rest of the components, including the Hall effect sensor and microcontrollers, receive a 5 volt output from a DC to DC converter mounted on a custom PCB. Early testing verified our weight was within our 35-pound limit, with 10 pounds of margin. Our pulleys met the required gear ratio range. And finally, our sensor was tested to be within 5% accuracy of the engine RPM. After our preliminary verifications were done, we moved on to testing our 2 core controllers. Our gear ratio controller was tested mid-February on the vehicle, and the RPM controller was then tested several times on asphalt and dirt terrain in March. All our testing requirements passed.
Since the bulk of the testing was completed early on, we decided to complete a performance study between the mechanical CVT currently being used by the Baja team and the electronic CVT developed in this project. We performed a series of tests in addition to the tests laid out in the initial requirements that focused on capturing key performance metrics of both CVTs for comparison. An acceleration, maneuverability, hill climb, rock crawl, and top speed tests were performed on both CVTs, and using the log speed, gear ratio, and engine RPM data, we were able to characterize the performance of the eCVT in comparison to the mechanical CVT. In tests such as acceleration and hill climb, the performance of the mechanical system was initially better, but after just a couple minutes and a code flash to the system, the performance of the eCVT was tuned to be equally matched.
Ultimately, in terms of tuning, performance, and controls, we found that the electronic CVT was successfully able to control the engine RPM and maintain it at peak power within margin. The miles per hour versus RPM was plotted to compare to the ideal CVT behavior. As you can see, the electronic CVT follows the ideal shifting path as the transmission is shifting. The mechanical CVT data was also plotted for comparison.
In conclusion, our design was able to meet all of the requirements that were identified at the beginning of the year. We were also able to successfully integrate the system onto the Baja vehicle and demonstrate a fully functioning off-road capable system. Clear project milestones set early on allowed for the success and completion of the project, which also provided time to expand the scope of our testing and validation. We were able to utilize collected data and tune and characterize the performance of the eCVT and showed that our system was comparable to the existing mechanical CVT. Once again, we are Team 22018. Thank you for watching.